Okay, so the more appropriate name for this should be solution equilibrium. Which mainly what we're going to look at is buffers and titrations. So a buffer, so you need to know that a buffer is it's a solution that's composed of a weak acid and its conjugate base, or a weak base and its conjugate acid. So a buffer is made out of those weak acid or bases and then its conjugate. Okay? The key thing about a buffer is that it resists large changes in pH upon addition of small amounts of hydrogen, or of an acid, strong acid, or a strong base. So it's going to try to keep, if it's at a pH of 8, it's going to try to keep that pH at 8 or around there, 7.95. Okay? That is what a buffer is. And it's just going to change it just slightly, change the pH just slightly. So if I were to have, say, H2CO3, this is going to be my example here. If I have H2CO3 and I add water to it, that's a weak acid, what is its conjugate base going to be? H2CO3. It's going to become HCO3 minus plus H3O plus. Okay, so this would be our weak acid and its conjugate base. So in my beaker, so here I have my beaker, I am going to have HCO3 minus floating around, and I'm going to have H2CO3 floating around. So that's my buffer. Okay, so my buffer, I have both those things floating in there. Now, what happens to this buffer if I add H plus to it or OH minus to it? Well, if I add H plus to it, who in this buffer, which one is it going to bond with? Which one is it going to interact with? HCO3 minus or H2CO3? So it's going to go with HCO3 minus, and we're going to make what? H2CO3. If instead of adding H to it, I add a strong base, a sodium hydroxide to it, a little bit, who's it going to interact with? Ooh. It's going to interact with H2CO3, and we're going to make what? HCO3 minus and some water. Okay, so we're just making whatever is in there when we add that strong acid or that base. And that's why we resist that change, that pH changes. The amount, right. So we can put this into a nice equation. It is called the Henderson-hasselbach equation. It is on your AP chart, so you do not need to memorize it. But it is the pH of a solution is equal to the pKa plus the log of our ion, concentration of our ion over our acid. Or if you're dealing with a base, the pOH is equal to the pKb plus the log of the concentration of our ion over our base. So, and remember, P just means negative log. Any questions on that? You could use rice tables if you wanted to. But if you know or can get to the Ka or the Kb, then Henderson hasselbach would be what I use.
So because these problems and these calculations, do these tend to be free response?
Yes. And usually you're going to guarantee that you're going to have at equilibrium, whether it's acid-base equilibrium or solution equilibrium, kinetics, thermo.
Because they're so big. So all your free responses tend to be like, that's just a small thing they can.
And that's why we try to do the heavy stuff, like what I've been doing at the beginning, because most teachers won't even get to it. So that's why I try to do it at the beginning.
When in doubt, x squared over molar.
I'm over here. All right, calculate the pH of a solution, which is 0.53 molar HC6H4NO2 and 0.5 molar NaC6H4NO2, and your Ka is 1.7 times 10 to the negative fifth. Jaden, we pass that over to Jaden, America.
Yes.
All right, calculate pH. So what are we dealing with? What kind of solution are we dealing with? Weak. It's a weak acid. And it's conjugate base. And they've added them together. So I would probably think to myself, this is a buffer. So if I know it's a buffer, then, and they're looking for pH, I know my equation that pH is equal to pKa plus the log of my ion concentration over my acid concentration. Huh? It's a weak acid, and then it's conjugate base.
Oh, okay.
So, pKa, so we need the negative log of our Ka, which is 1.7 times 10 to the negative fifth, plus the log.
Are we supposed to be able to see that? Okay.
Yeah, it's not on that sheet.
Oh, I'm sorry. Just write it down to the side. What's the ion? Ion is 0.5 molar over 0.53 molar. So what is my pH? We have 2 sig figs, so we need 2 decimal places. 4.74, yes.
Wait, it's ion over acid.
Uh-huh.
Doesn't even matter. I got it.
Oh, because the conjugate base is just the C6.
And we have 2 decimal places because there were 2 sig figs and Ka.
Yes. Not Ka. I don't do the Ka at the concentrations. I look at the concentrations, since those are constants. All right. Next. Calculate the pH of a solution that is 0.245 molar NH3, which is what type of solution? A weak base. And 0.245 molar NH4NO3. So if we're dealing with so it's a conjugate acid. And the Kb is 1.8 times 10 to the negative 5. So I can't go straight into pH because we are dealing with a base. So POH is equal to pKb plus the log of our ion concentration over our base concentration. So that means we have the negative log of, I have 1.8 times 10 to the negative fifth for your Kb, plus the log of our ion concentration, which is 0.245, over base, which is 0.245. So 4.74. So here, pH equals POH equals PKB, right? So POH is 4.74, y'all said? So pH is 9.26. We have 3 sig figs, so let's go 3 decimal places. Is it 5.3 or 5.5? When you see something and the concentration of your acid or your ion over the base or ion over the acid is the same, we call this an effective buffer. When the concentration of our ion is equal to the concentration of our acid or our base, it's an effective buffer. So it's going to really resist that change. And our pH equals our pKa. Questions on that? Do we want to put it in a rice table to see how we would do it if it was a rice, or no?
Sure.
Yeah? All right. Okay, so if we were to do this, I'm going to erase what I have here, and we're going to put it into a rice table. Okay, so we have we're starting out with NH3. So if we're doing, we have NH3. And we have to add, we end up with NH4 plus. Yeah. Yeah. So I take my weak base and I add it to water. Remember, we always take our weak base or weak acid and add it to water. And we end up with our conjugate, and we end up with OH minus. So that's the R in our rice table. Initially, how much of NH3 do we start out with? 0.245. And how much of our NH4 do we have? 0.245. Water goes away. We have no OH minus in there. Which way is this going to shift? To the right. So we have minus X plus X plus X. We end up with 0.245 minus X, 0.245 plus X, and X. X is negligible, so we can cross that out. And then we're ready to say that KB is equal to X over 0.245 over our reactants, which is 0.245, and solve. So KB is equal to X. And we know that KB is 1.8 times 10 to the negative 5, which is equal to X, which is equal to our OH minus concentration. Which takes us to a POH of 4.74 and a pH of 9.25. Henderson Hasselbach, so much more easier, yes? Yes, okay. But you can choose what you want to do. All right, let's do number 3. calculate the pH of a solution prepared by mixing 20 mils of 0.3 molar acetic acid with 20 milliliters of 0.335 molar sodium acetate. So we have a weak acid. And we are dealing with its conjugate base. But what else do we see? What is the problem here? It's 20 milliliters. What do we need to do if we have 20 mils of 0.3 and we add to it to 20 mils of 0.35? What happens to our molarity? Our molarity is going to change, right? So we need to do a dilution. We need to figure out its new molarity. So 0.3 times 20 is equal to our new molarity, and our new volume is 40. So our new molarity of our acetic acid is 0.15. And we go and we do the same for our acetate ion. So we have 0.35 times 20 is equal to molarity times 40. So our new molarity is 0.175. All right, now we're ready to do either Rice-Tabor or Henderson-Hasselbach. What do y'all want to do? The equation. So we're dealing with acids. So pH is equal to the negative log of our Ka, which is 1.8 times 10 to the negative 5 plus the log of our ion, 0.175, over our acid, which is 0.15. And our pH to 3 decimal places. 4.812.
So we put our weak at the bottom?
The acid, the weak acid or weak base goes on bottom. And then its ion, its conjugate, is on top.
And then say they gave us K, we gave us an acid, we would just divide K for 1 times
All right, let's look at this next one. B, specify the reagents and specific concentrations of each reagent to prepare a buffer solution, so keyword, buffer solution, which would have a pH of 4.19. So, the Ka, so what I would do is I would go and see, I really don't like this problem here. Well, I'll do one on your homework that I like better. So we're going to delete this and see homework.
We're not going to come back to this,
No.
right?
I'm just going to put C homework 6A problem 5. That will be your example for that. All right, given a solution of ammonium chloride, what's the formula for ammonium chloride? Ammonium chloride formula. NH4Cl. What additional reagent? Okay, a reagent, all that is just a solution. If I have to go and get all my reagents, it's all my solutions and whatever I'm using to do this lab problem. Yes?
That is not number 5.
I'm going to go back to 5. Oh, sorry. I'm going to do that after we do this. You guys had me confused. Sorry. All right, so what additional reagent or reagents, those are just solutions, whatever things we need to do this lab, are needed to prepare a buffer from ammonium chloride. So keyword, buffer. So if I have NH4Cl, what do I need to make a buffer? So what is if you have ammonium, that's my conjugate, did it come from?
Wait, that's the conjugate water.
NH3. All right. So I have my solution here. I have my NH3 and I have my NH4 in here. If I add a bunch of H plus in there, all right, so I'm looking at A. If I add a bunch of H plus in there, who is it going to interact with? NH4 plus or NH3? NH3. And what's it going to make? NH4 plus. So we have the strong acid, and we add it to this weak base, and what do we end up making? We end up making a weak acid. Huh? Yeah. If it wants to resist that change. What if we add base to this? So what if we add, we add a strong base, so we add a hydroxide in there. Who's it going to interact with? NH4 plus. And we're going to make some water. And what else are we going to make? NH3. So this time, we have a strong base interacting with a weak acid to make a weak base.
And this would be that would be a good explanation.
Mm-hmm.
Because it says explain to
Yes.
It would be like a sentence you just write the equation.
Yeah, explain how this buffer solution resists a change. What if a portion of this buffer is added to equal amounts of water? What would happen to our pH this time? So if I just add water into there, what's going to happen? Well, if we have our pH is equal to the pKa plus the log of our ion over the acid or base. Oh, POH, yes, thank you. If I add water to that, what's going to happen to the ratio of this to this? Stays the same. So what happens to our pH? Nothing. pH is unchanged. The ratio, if I add water to this, then the ratio of this is a ratio. So this might go down and this one's going to go down. So the ratio stays the same. So pH is unchanged because ratio is the same.
Wait, why would you have NH4 on top and not NH3?
Yeah, one's the ion and one's the base.
Oh, yeah.
I mean, I could flip it and it would be pH with NH3 on top and NH4 on bottom. It doesn't matter. I mean, for this problem, it's just a hypothetical what's going on. Then we're looking at the POH. So if I change this to pH, then this ratio is going to flip. Okay. And lastly, this is a problem from 1983. AP exam. So this is way before the redesign. Specify the properties of a buffer solution. So what do we know about a buffer solution? What is a buffer solution? So a weak acid and its conjugate. Sorry, that's really small. Or a weak base and its conjugate. But, so it has to be able to, so we know that these resist changes. So what, oh, we just said that. So it needs to resist changes, and I just had something written, and I forgot what it is. So yeah, the concentration of our HA has to be equal to the concentration of our A minus, or our base concentration is equal to its conjugate base, or conjugate acid. So those concentrations are equal. So what can we say about the pH? If those are equal, what can you say about pH? Yes. So pH is equal to pKa. Yes. Yeah, that's why I kept on saying, oh, maybe I should have put this on that one. Questions on that? All right. So.
Why does it equal? Okay, never mind. I got it.
You got it?
Yep.
All right. An employer is interviewing 4 applicants for a job as a laboratory technician and asks how to prepare a buffer solution with a pH close to 9. So Archie A says he would mix acetic acid and sodium acetate. So we have acetic acid. We have acetic acid and sodium acetate. Beulah B says she would mix NH4 and hydrochloric acid. Carla C says she would mix NH4 and NH3. While Dexter D says he would mix NH3 with NaOH, which is given the appropriate response. So who's going to get hired and why? Who's going to get hired and why? Carla. Why is Carla going to get hired? That's a buffer solution. Okay, so let me change this color. This is a buffer. So we had 2 buffers, right? Yeah, Archie and Carla both had buffers. So why is Carla's right and Archie's isn't? Why is Carla's right and Archie's isn't? Because
it's a base, right? That's when the pH was 9, which would be a basic solution.
right. So it's a pH of 9, which means we need to have a basic solution, and one of these is made out of an acid and its conjugate base, and one's made out of a base and its conjugate acid, which would be Carla's problem, or what Carla did.
So Carla used a base and its conjugate acid.
Yes. So that would give me my pH close to 9. And of course, they give you extra information in there that says no calculations are needed, but here you go. Any questions over that? Everybody good? So homework, let's get our homework out and take a look at that problem, number 5.